Good morning. Today we will talk about how to remove the dimensional reductionality using principal component analysis. So I'm going to use the dataset, the default dataset iris in R. Run this line. Okay. So let's explore this dataset. So this dataset has 150 observation and 5 column, where the first 4 columns they are independent variable and the last column is the factor variable. So sepal length, sepal width, petal length and petal width, these are the independent variables, whereas species is the factor with the 3 levels, that is setosa, versicolor and virginica. Okay. We'll try to find out the structure of this dataset by using this line. So it says that the data frame has 150 observation and 5 variables. So these are the 5 variables: sepal length, sepal width, petal width and species. So species is a factor variable, whereas these remaining 4 variables, they are independent. Let's run this line to see the summary of this data set. So this gives you the minimum and maximum value for each variable. So minimum value, the default minimum value for the sepal length is 4.3 and the maximum value is 7.9, whereas the default minimum value for sepal width variable is 2.0 and the maximum is 4.40, and that too for petal length it is 1.0, the maximum is 6.9, and for petal width it is 0.1 and the maximum for petal width is 2.9. Whereas there are 3 levels for this factor variable species, which is setosa, versicolor and virginica. So in machine learning, we know that we pre-process the data, that is we partition the data into 2 data sets. One will be used for training the machine learning model and the other data set will be used to evaluate or to test the machine learning model. So I'm going to use this function seed, which ensures that there won't be any duplicate instances in the train and test data set. So I will set this seed to random with some random number 112. You may choose some other number. I took this object independent in which my splitted array will be stored. Okay. I'm going to use this function sample to partition this data iris into 2 data sets, train and test. So this number 2 will indicates the number of splits. So I want 2 splits for this data set iris. The n row indicates the number of rows. So the number of rows in iris, there are 150 rows. So I want all the 150 rows. So replace parameter, this argument is set to true, and this is probability, it is set to 0.8 and 0.2. So here this indicates that I want the 80-20 splits. Okay, so 80% instances out of 150 will go into training data set and remaining 20% instances will go into test data set. So I have created here the object training in which all the train instances will be copied. So the data set in which this 150 instances are there is iris in the bracket independent one, that is the first independent object out of this 2, okay, which has 80% of instances that will be copied into train variable, and there is a second array, that is independent second array, which have the 20% of instances that will go into testing. So let's run this line. Okay, so you can find the train data set, this train data frame, it has 113 observation, that is 80% of instances, whereas this test object, it has 37 observation, which is nothing but the 20% of this 150 instances in the iris data set. Okay, now to create the scatter plot, we have to run this library called psych. Now why I want to create the scatter plot? Because I want to show the correlation between the variables. I want to see the correlation between the variables. So let's run this library called psych. Okay. So I will create the scatter plot using this function pairs.panel, and I want to create the scatter plot for the data set training. I do not want to use the last column, that is species, because it is a factor variable, and it's not meaningful to include the factor variable in the correlation scatter plot. Okay, so I excluded this last column, species. The gap I want between the scatter plot to be 0, and I want to color code each of the species from this training data set. So red, yellow and blue, I want to use these color codes, and this PCH is set to 21, which decides what symbol for each instance to be appear on the scatter plot. So let's run this line. Okay, so this is the scatter plot for all the 4 variables: sepal length, sepal width, petal length and petal width. The lower triangle of the scatter plot is nothing but the scatter plot between the variables, whereas the upper triangle is nothing but the correlation coefficient. You can observe that the correlation coefficient value, it lies between negative and positive. One can easily find here the correlation coefficient between the sepal length and sepal width is negative, that is minus 0.8, whereas the correlation coefficient between the sepal length and sepal width and petal length is minus 0.47. So there are 3 positive correlation coefficient in this upper triangle, which has the value 0.87, 0.80 and 0.96. So this 0.96 is the higher value, higher correlation coefficient value amongst all. This indicates that the variable petal length and petal width, they are highly correlated. That means they have very less variance between them, and you can observe that this correlation in this scatter plot of petal length and petal width. So one can easily see that this petal length and petal width, this correlation, these 2 variables, they are highly correlated. That means they are very less variables from each other. Now in machine learning, we know that if the variables are highly correlated, then that leads to the problem of multicollinearity. So because this petal length and petal width, they are highly correlated, so this leads to the problem of multicollinearity. And the principal component analysis is used to solve this problem of multicollinearity, or to resolve this problem of multicollinearity and reduce the number of dimensions of your data set. So this clearly this information of scatter plot, it will help us that all the 4 variables cannot add the contribution to my model. So there are only 1 or 2 variable that gives the high confidence or a high contribution in building the machine learning model, and that's nothing but the dimensional reductionality, and we are achieving this dimensional reductionality using principal components. Okay, so to create the principal component, I'm going to use the function prcom. So pr stands for principal and com stands for principal component. Okay, and I will save this principal components into the object called PC3. Again, to create the principal component, I'm not going to consider the last column, that is species, because it is a factor variable. Okay, I want to keep the center to true. That means I want all the variables to be converted into average 0, whereas the scale of all the variables to be true. That means I want all the variables to be normalized. Let's run this line. Okay, let's see what are the attributes of this principal components. So the attributes of the principal components are standard deviation, rotation, center, scaling and x values. Okay, so let's see what value lies in the center. So if you run this, okay, there is some error. This value is actually inside the function. So let's run this line to find out what value that center contains. So the center variable, it is nothing but the mean of each variable, that is sepal length, sepal width, petal length and petal width. So the mean for sepal length is 5.91, whereas 3.09 for sepal width, 3.85 for petal length and 1.23 for petal width. The same way we can also find out the scaling for each variable. So scaling for that is the normalized value for the sepal length is 0.83, whereas the normalized value for sepal width is 0.41, and that too for petal length is 1.81 and petal width is 0.77. So these are the different ranges of value, or you can say the different scales for each variable, and that's the reason why we want to normalize each variable, because one variable should not overshadow the other variable. Okay. We can print the values of the PCs. Okay, so we can have the standard deviation for all the variables, rotation, which is also called as the loadings for all the variables, and these are the different values for the variables and the corresponding principal component. So this rotation is nothing but the 4x4 matrix, where sepal length, it corresponds to the principal component 1, sepal width correspond to principal component 2, and that too for PC3 and PC4 it correspond to petal length and petal width. Now if you observe the first column, that is, if the value of PC1 is increased, then the value of this petal length and petal width is also increased, whereas the value of sepal length is also increased. But surprisingly, you can notice here that as the value of PC1 is increased, the value of sepal width is decreased. So if you remember the scatter plot, where the sepal width has the negative correlation coefficient, which is highly variable as compared to the other variable, whereas this petal length and petal width, they are highly correlated, and that's the reason they are very less variable with each other, and the value of this petal length and petal width, they are higher than the other variables. And same is the case for this PC2, PC3 and PC4. Okay, so let's go to the summary of this components, principal components. So in summary of principal components, there is a standard deviation for each principal component, there is a proportion of variance, and there is a cumulative proportion. So proportion of variance of PC1, which explains the high variability amongst all the variable. So PC1, it explains about 73% variability amongst all the variable, whereas PC2 explains the 21% variability, and this variability, it is decreases for PC3 and PC4, which indicates us that, which gives us the meaningful information that the principal component 1 and principal component 2, which has the major contribution in building the machine learning model, whereas this PC3 and PC4, they do not have any contribution, they do not have any confidence in building the machine learning model. So we'll try to see how this principal component is used to remove the multicollinearity problem. So again, we'll try to plot the scatter plot for all the 4 variables. So let's run this line. And here one can notice that the correlation coefficients, they are 0. That means we have removed the problem of multicollinearity. Okay, in the next video we'll try to see how the biplot is created for all the 4 variables to represent the variability amongst the variable.